Hi guys, this is Mrs. Harlan, and today we are going to be looking at the probability decathlon from the alternative learning plan. I know that you guys have been working through Khan Academy to learn about probability, and so I just wanted to walk you through these so you can have an understanding of how we normally do these problems, what these problems look like. So number one says the names of 6 boys and 7 girls are written on cards and placed in a hat. You pick one card, and without replacing it, you pick another. What is the probability of picking 2 cards with girls' names? So in this situation, we have 6 cards that have boys' names. So 1, 2, 3, 4, 5, 6. And we have 7 cards that have girls' names. 1, 2, 3, 4, 5, 6, 7. So we have 13 cards that we could pull out of this hat. And there's a chance that it could be a boy's name or it's a chance that it could be a girl's name. We want to know the probability that we pick a girl's name and then we pick another girl's name. So first we need to determine the probability that we pick a girl's name the first time. Well, we know that probability is written as a ratio, and the top should be our intended outcome. It's what we want. So since we want a girl's name, we know that there are 7 girl names available. Now, the bottom of our ratio is how many total outcomes there are. Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total cards. So there are 13 total outcomes. Now, when we want to find the probability of something happening and then a second thing happening, we're going to have to multiply our 2 ratios together. And we need to make another fraction. Now, here's the interesting part. This says without replacing the card. So in this scenario, we take one of these girl cards and it's now gone. So keeping that in mind, when we find the probability of another girl card getting chosen, that other one isn't in there. So if we want to find the number of girl cards that we could pick from, now there's only 6. 1, 2, 3, 4, 5, 6. And when we're talking about the number of cards that there are to choose from, there's no longer 13. There's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This highlights the difference between independent and dependent situations. This is a dependent situation because the denominator changes. We go from having 13 cards to 12 cards, from 7 girl cards to 6 girl cards. So now that we have a probability of getting a girl card the first time and the probability of getting a girl card the second time, we multiply them together. Now to multiply fractions together, we just multiply across. So 7 times 6 is 42, and 13 times 12 is 156, so our answer is B. Now I know I mentioned this the other day when we had a group on Zoom, but you do not necessarily have to simplify with probability. So that a fraction like 42 over 156 is perfectly acceptable. Number 2, let's get a highlighter. 11 letters spelling probability are placed in a bag. You pick one, you replace it, and then you pick another. What is the probability of picking P and then I? So basically in this bag, we have a card that says P, R, O, B, A, B, I, L, I, T, and Y. And these are all different kind of cards or chips placed in the bag. So we want the probability of picking a P and then an I. So first we need to find the probability of choosing a P. So our desired outcome is P, and there are 1 of them, just 1. And then we need our total outcomes, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So the probability of choosing a P is 1 out of 11. Now, since we are finding the probability of one thing and then another, we multiply. Now here's where it gets interesting. In number 1, we took the card away, but we didn't replace it. But in this problem, we do replace it. So that's like saying we took out the P and then we put another one, we put it back. So in this situation, the number of total letters doesn't change because we put it back. This is an example of an independent situation because the probability of the second event doesn't matter what happened in the first set. So again, we are looking for the letter I now, and I see 2 of them out of 11 possible outcomes, and we multiply across the top and bottom. 1 times 2 is 2. 11 times 11 is 121, so that gives us D. Number 3, 1 marble is picked from a jar without looking, so that means it's random. If a jar has 4 blue marbles, 3 green marbles, and 2 red marbles, what is the probability of not red? So just as a reminder, that notation with P and the parentheses, P stands for probability, and whatever is in those parentheses is the probability that we're trying to look for. So we want to find the probability of choosing a not red marble. Well, as far as I know, blue is not red, green is not red. So we have 4 blue marbles. Let's draw a little picture. And we've got 3 green marbles. And we've got 2 red marbles. And if we look at our picture, there are 1, 2, 3, 4, 5, 6, 7 marbles that are not red. That's our desired outcome. Out of 1, 2, 3, 4, 5, 6, 7, 8, 9 total marbles. Number 4, Nelson is learning the difference between independent and dependent probability. Select all scenarios that show an example of dependent probability. So this is kind of what I want to emphasize in our time together today. Independent probability is situations where there is replacement. So you take something out of a pile and you put it back. You do 2 things that don't affect one another. Like you flip a coin and you roll a dice. So if I do those 2 things, nothing's going to change either time. Dependent variable is where there is no replacement. So this might be a scenario where you pull something out of a bag and you put it to the side, or you pull a sock out of a drawer and you put it on your feet, or you take a gumball out of a bowl and you eat it, and then it's not there anymore. So if we look at number 1, it says picking a piece of candy from a bag and then a friend picking a piece. So in this situation, let's say there's 5 pieces of candy in a bag. You take one of them. Ooh, you didn't take 4, you only took 1. Let's make my eraser a little smaller. You take 1. Now there's less options for your friend to choose from because you took it and you kept it. So this is a dependent situation. The second option says drawing a card from a deck, replacing it, and then drawing another card. So again, this is where we're replacing it. So if I draw, let's say we have 5 cards, we'll keep it easy, small numbers. If you take a card from the deck, but then you put it back, you replace it, your number of outcomes doesn't change. So that's independent. Spinning a spinner twice. So if anybody has ever played the game of life, this is really similar to the game of life. You have a spinner like this. You guys had that Desmos activity with a spinner. It kind of looks like this. Oh, I'm a terrible artist. You guys know that. If I spin the spinner, nothing changes. We don't delete any of the wedges. We can't not use any of the spaces anymore. So when we spin it again, the number of outcomes is still the same. So on this spinner here, there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. But no matter how many times I spin the spinner, it's going to be the same number of outcomes. So that is an independent event. Number 4, selecting a prize from a bag, then turning to another person to let them select a prize from the bag. So this is just like the candy. You have 5 prizes in the bag. You take one, and then you turn and let somebody else take a prize. Well, now that you've taken a prize out, there's one less for them to choose from, so their probability is different. So that is dependent. Finally, rolling a number cube 5 times. So a number cube is like a dice we use to play a game. If you roll the dice, you have a 1 in 6 chance of getting any of those numbers. If you roll it again, you still have a 1 in 6 chance of getting any of those numbers. And no matter how many times you roll the dice, the probability is the same because the dice doesn't change. You don't erase the sides. So that's why that is an independent situation. Number 5. Coral reef fish occur in groups of 3 male and 12 females. Jacques Cousteau nets just one of these fish. What is the probability that it is male? So this is just simple probability. Our desired outcome is male, and there are 3 male, so we put that on top. 3. Now our total number of outcomes is including both male and female, so we add them together, and 3 plus 12 is 15. So that is our ratio written as a fraction. Now probability can also be written as a percent. So let's use Desmos to do our division to turn this into a decimal. So 3 divided by 15, we get 0.2. And if we move that decimal point 2 places to the right, we get 20%. Number 6, 4 cards marked G, H, J, and K are shuffled and placed face down. What is the probability of drawing the card marked G? So the reason they make a point to say it's face down is so that you know it's random. Obviously, if we could see the cards, it would be 100% probability. But here it's random. So our desired outcome is G. So we say, how many times could I get G? And since there's only one, our numerator is 1. And then we want to talk about our total outcomes. How many possibilities are there? Well, I see 1, 2, 3, 4. So our probability is 1/4. So here we have a spinner. It says the spinner is spun once. What is the probability of spinning the letter X or T? So now we need to find how our desired outcome is either X or T. It doesn't matter. So we can include both X's and T's when we count them up. So we've got 1, 2, 3, 4. Then we need our total outcomes. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have a 4 out of 12 chance of getting a X or a T. Now we don't see that in our answer choices, so we have to simplify. I can divide both 4 and 12 by 4. 4 divided by 4 is 1. 12 divided by 4 is 3. So we get 1/3. Number 8 says the spinner is spun once. What is the probability of not spinning the letter U or Z? So first we need to count the number of letters that are not U or Z because that is our desired outcome. So we have 1, 2, 3, 4, 5, 6, 7. And if it makes you guys feel better, the first time I did this question, I accidentally started counting the Z's and the U's, but we want the not letters. So we have 7 of our desired outcome. Then we need the total number of outcomes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 7 out of 12. Number 9. A package contains 7 bags of tortilla chips, 3 bags of cheese puffs, 4 bags of hot fries, and 6 bags of potato chips. So we got a lot of snack food going on here. If Stephen reaches in the package and chooses a bag without looking, we want the following. We want the probability of choosing hot fries. So our desired outcome is hot fries, and we have 4 bags of those. So that's our numerator. For our total outcomes, we need to add up the total number of bags of chips. So 7 plus 3 plus 4 plus 6, so that gives us 20. Now when I'm looking at my answer choices here, 4 out of 20 is not an option. So I have to simplify my fraction. 4 divided by 4 is 1. 20 divided by 4 is 5. So we get 1/5. Now we want the probability of him choosing tortilla or potato chips. So we need, our desired outcome is tortilla or potato. So I need to add 7 plus 6, that's 13. And our total number of chips stays the same, so that's 20. And number 10, Dave is a member of a bowling league. The table below shows his record for the last 10 games he bowled. So that's 100 frames. Based on his previous record, what is the probability that Dave will bowl a strike in his next frame? So our desired outcome is the number of strikes over the total number of outcomes. Well, it looks like based on this chart, he normally makes 12 strikes. And if we talk about out of his total, remember it's not 10 games, we're looking at the number of frames. So that's 100 frames. But when I look at my answer choices, 12 out of 100 is not an option. So I have to think, what can I divide both 12 and 100 by? And that's 4. 12 divided by 4 is 3. 100 divided by 4 is 25. So it's C. Now that you've watched this video, you're going to try some on your own. But before that, for this assignment, I want you guys to make a flip grid telling me one thing you learned during the video today.